Hi there, welcome to this lecture series on matrix algebra. This is lecture 35, part 1. The topic is on linear systems of ordinary differential equations, and we call that with an abbreviation ODE. Here in particular, we will use what we have learned on matrix exponentials and apply the concept to solve linear systems of ODEs. Let's get started. Let's first look at the vector field determined by matrix A. Here the matrix A is a square matrix n by n, and then at each point you can do the multiplication A times x, and it will give you a vector also in Rn, and we can thus draw the vector. Let's take an example. So we have an A matrix, which is like this. Then A times x, where x is a vector x1 and x2, and you can carry out the product, and then you will get x1 and negative x2. Since this is a two vectors, so it's a two-dimensional space, and we can therefore visualize everything in the plane with the x1 axis and x2 axis. And then at every point, let's say a point here, and then you find its x1 value and x2 value of this product A times x. So x1 value will be just x1, and the x2 value is negative of x2. So for example, this point here, it would be a vector in this direction, but then the x2, meaning the y-axis, will be reversed. So instead of pointing up like this, and you have to point down. And then similarly, a point down here, the vector x would point in the direction, in this direction, but then the y-axis will be flipped in this product A times x, and then you will flip and point upwards. So here we showed all these vectors determined by A times x at various points to see that how all the directions are being pointed. Another example, A matrix takes this form, and it's 0 on the diagonal and 1 down here, negative 1 up there. Then A times x, you can carry out the product, and you will get it's negative x2 and x1. And then again, we can visualize this in a two-dimensional plane. So we can, for example, take some points along the x1 axis. Let's say this point, let's say it's 1, 0. And then what is A times x? We see that x1 is 1, x2 is 0, so it's 0, 1, therefore a vector pointing upwards. And then in fact, all of these, let's say the x1 is A, x2 is 0, here it's A, and then you will have 0A and pointing upwards. And similarly on the negative x1 axis, and you will have let's say negative A 0, and then inverted will be 0, negative A, so you will be pointing downwards. And then a similar argument will show you that on the y-axis, on the x2 axis, they will point to the left on the upper half and to the right on the lower half. And then you can also find some intermediate value and then draw these directions of vectors. Now let's talk about systems of linear differential equations. We can interpret the differential equation graphically as follows. So xt there is the position of some point which moves in time, and this is its position at time t. And then A times x of t here would be the velocity, how fast and in which direction that point is moving. Some terminology, when we say a Cauchy problem, that means more or less an initial value problem. So given an initial position at time, for example, t equals 0, and we wish to find the entire trajectory of that point that's moving following the description of your differential equation. So in other words, the Cauchy problem will be the following. So find the solution to the differential equation, that is, the derivative of x as a function of t here is determined by a times x of t, where the initial condition x at 0 is given at some point x bar. This is a given number. And now we can use the graphics we have drawn earlier when indicating the direction vector of the right-hand side of the ordinary differential equation at every point, and roughly sketch the solution. So for the first example, these blue arrows are the vectors a times x at every point with the different x values. And let's say now we have an initial condition is here. So x at 0 is at that point is x bar. And how does the solution evolve? Well, at that point, we see that the vector field is pointing downwards. So you're going down. And then as you go further down, and the vector field gets a bit less steep and gets more and more horizontal. And then you would follow this direction and you would bend, and then you would approach the x1 axis as time grows to infinity. And then a similar graph, a trajectory kind of a sketch, can be done on this quadrant. You will have an initial condition, for example, here. Then you will come down, and then you will bend to the left, and then you will approach the axis. And down here will be the same, symmetrically. You come up, and then you would get flatter and flatter and flatter. And same here, you would go this way. So we don't know exactly how to write out the function of the solution, but from the graphics, we know its property and we know how it should evolve. Let's look at the second example where the vector field AX is sketched here in blue arrows. So let's say we have an initial condition x0 is x bar, some point here. So how does it go? Well, so here the vector says it goes up, so you go up, and then the vector says it goes up less, and then it turns, and it will cross here horizontally, and then the vector field will point down, and then you will go down, and then so on and so forth. So it will be something like that. And probably you are guessing from this bunch of arrow, probably it's going around in a circle. And in fact, it does. And now we consider a model. It's a linear differential equation in the end, which we use to model the population growth in time. So the setting is the following. Xt will be the size of a population at time t. And then A denotes the growth rate, which is a constant. And then you are given x0, which is x bar, that will be the initial population at time 0. For such a model, the growth is described by the following ordinary differential equation. So the rate of change, d dt, of the population x of t equals to the rate a times the population x of t. So we call this ODE. For such a problem, one can find an explicit solution. Explicit, we also call an exact solution. Explicit means I can write it out as a function clearly. So the function would be e to the power a times t times x bar. One way of making sure that this is a solution is to plug it back in and verify. So we want to plug back into the differential equation as well as the initial condition to make sure they are both satisfied. So let's check the initial condition. X is 0 is supposed to be x bar. So this will be put t to be 0. So e to the 0, x bar, and e to 0 is 1. It's just x bar. And then let's put back into the ODE. So we start from the left-hand side and want to show that we'll reach the right-hand side. So d dt, let's put in a function for x of t, which is that. And remember, this is a constant, so you are just differentiating the exponential function, where you can just take a times e to the t times a. And then we see that e to the t times a, that is just x of t, so I get a times x of t. So the ordinary differential equation holds here, and therefore this is a solution. The next example is a model for simultaneous growth of two competing populations. So there are two species living in this environment and they are competing for resource and space. So here's the setting up. So x1t, x2t, they are sizes of two populations at time t. And then x1t at t equals 0 initially is x1 bar, and then for species number 2 it's x2 bar, which is x2 at 0. So initial population at t equals 0 is also given. Now we assume that the growth is described by the following system of ODEs. So the rate of change for x1, ddt of x1t, is 3 times x1 minus x2, and the growth for x2 will be ddt of x2 is negative 2x1 plus 2x2. So what is a physical interpretation of this equation? Let's take a look. So for the first equation here, it says that the population for x1 is changing following this formula. Let's consider the case where x2 is 0, meaning x1 is there alone without x2. And then we see that it is just the exponential growth for x1 if it's by itself with the rate 3. And now x2 is non-zero, so how does it affect the population of x1? Well, since they are competing for resources, then x2 would have a negative effect on the growth of x1 and therefore is negative. And then the number in front of it, here is 1, is how strongly it affects it. So here is 1, let's say it's moderate, and because its own growth rate is 3, so it's growing faster. Okay, so a similar analysis can be done to the second equation. So the growth of x2 in the absence of species x1 will be exponentially growing with the rate 2. And then if x1 is present, it will have a negative effect for the population of x2. And how strongly it affects is this number negative 2. So it's the same as how much itself would have grown. So we see that the right-hand side here is a linear system. So if it is a linear system, then we can write it in matrix vector form. Let's form the vector x to have two components, x1 and x2. We call this vector x of t. And then d over dt is the derivative. And then the right-hand side here can be written as the product of the coefficient matrix times the vector. And then the coefficients are the coefficients we collect, 3, negative 1 here, and negative 2, 2 here. Okay, and then you can give the initial condition here would be the x at 0 is this x. Let's write it as a capital boldface x bar. Okay, so very compactly we can write it as this ODE in matrix form. So this motivates our study of such a problem in a general setting. Let's say we have a linear system of ODEs in general, so we can write it out like this. The time derivative of the x vector equal to some A matrix times x, where A is a matrix of coefficients and x is your variable, and with initial conditions given. If you write everything out, then it takes this more complicated looking form. So x could be a vector with n unknowns, so it's in Rn, and then A is an n by n matrix times x, and then initial condition is a vector in Rn x bar. So how do you solve this equation? So let's take some hint from the scalar equation, and let's claim that the solution here is also explicit, that we can write out, where x of t is e to the t times a x bar. So we introduce this exponential of the matrix here, a times t. And then what is this a times t? Well, we can use the Taylor series of that and expand it. So this will be a summation k from 0 to infinity of this term here, t to the k, a to the k over k factorial. And if you write out the first few terms, then you will get k equals 0, you get identity, k equal 1, you get t times a, and k is 2, you get t squared a squared over 2 factorial, which is 2, and t equals 3 will be t cubed a cubed over 3 factorial, which is 6, and so on and so forth. Okay, so let's summarize our claim. We claim that a function like this would satisfy this initial condition and these systems of ordinary differential equations. Let's verify if that's true. So let's first check the initial condition. X of 0 would be putting 0 here, and then e to the 0 is the identity matrix, and then you get x bar. So initial condition is satisfied. Now we want to check the ODEs. So let's take the derivative of just the term e to the ta and see what I get. So d dt of e to the ta is d dt of the Taylor series, assuming that it holds, of this. So it's this series summing for k from 0 to infinite of this expression. And then let's assume that I can move the differentiation into the sum here. So I would take d dt of this and sum it up. And then inside here, that's the only term with t. The others are considered constant. So I'll be differentiating that, which will give me k times t to the k minus 1. And that holds for all the terms where k is from 1 to infinity. For the term when k equals 0, then I get actually 0. So this summation now is for k from 1 to infinite. Now we can simplify a little bit more. We see that I have a k on the top here. I have k factorial, which is just k times k minus 1 times k minus 2, and so on and so forth. So there is a k that will cancel the first k, and I will just get k minus 1 factorial. Then I copy the t to the k minus 1 here, and then I will write a to the k as a times a to the k minus 1. So I express this in a different way. Now in this expression, I'm going to change a bit the index because I see that I have k minus 1, k minus 1, and k minus 1 everywhere. So let me call this j. J is just k minus 1. So summing from k from 1 to infinity in j would be from 0 to infinity. So I would change this to t to the j, a to the j, and j factorial. And then I have matrix A, which doesn't contain any index, so I can pull it out. So I'll have A times the summation here, j from 0 to infinity of this expression. And then we recognize that this summation here, if I now write the j back into k, it's just an index. I can call it anything, right? And then we see that this is just the exponential of ta. So I have a times e to the ta. Okay, so we can use this, put it back into the differential equation, and we have that the derivative of x of t dt, if x of t is this e to the ta times x bar, so we'll be differentiating that. And then x bar is just a constant, so I keep, and then d to the eta is what we just did, so I copy it down, then I have that. And then I see this term here, x bar times e to the ta is just our xt, so I get a times xt. So which means that this x here satisfies the system of ODEs. And therefore, it satisfies the initial condition together, then we say it is the exact solution. Okay, so now we have a formula for the explicit solution of the ODEs, and then we'll continue our discussion in part 2. So I hope you enjoyed this part, and I'll see you later.